Hello everyone, today we're going to talk about centroids. We're going to be going over the theorems of Pappus-Guldinus. Here's the statics textbook that I used to get these information. So let's jump right in. First we'll be talking about surface of revolution. This is a very key concept. So surface of revolution is a surface that can be generated by rotating a plane curve about a fixed axis. So examples of these are if you rotate a semicircle, you get a sphere. If you rotate this line, you get a cone. If you rotate a circle, you get a torus. We can see a hollow sphere in the form of beach balls, hollow cones in the form of ice cream cones, and then hollow toruses, as in this diagram of a hollow torus over here. We can also have bodies of revolution. A body of revolution is a body that can be generated by rotating a plane area about a fixed axis. So we can have rotating a semicircle area, rotating a triangle, and rotating a circular area. So basically for the sphere, we can have billiard balls. For the cone, we can have solid cones, which are made of wood. And then for the torus, we can have donuts. So applications, well, we can apply these over here. The storage tanks over here shown are bodies of revolution. Thus, their surface areas and volumes can be determined using the theorems of Pappus-Guldinus. So the theorems of Pappus-Guldinus, there are two parts. Two theorems. Theorem 1, which talks about the area of a surface of revolution is equal to the length of the generating curve times the distance traveled by the centroid of the curve while the surface is being generated, like over here. We'll go into more detail about theorem 1 now. The area of a surface of revolution is equal to the length of the generating curve times the distance traveled by the centroid of the curve while the surface is being generated. A way to understand this is if we have a line L of length L, and then the centroid of that line is along the middle of that line. And then we have another line L because we rotated that line about the y-axis. The height of this cone is h, and then we have radius r. Over here the radius is r over 2. And then L is equal to the square root of r squared plus h squared. And the circumference of the circle generated by rotating the centroid is equal to 2 pi times r over 2. So basically this circumference. And then that is equal to pi r. The surface area of the cone is thus equal to pi r times the square root of r squared plus h squared. So and then generalizing to integrals. We have that the area is equal to the integral of 2 pi y times the differential element dl, a very small length. So 2 pi y is the circumference of the circle. We get the y from the curve, and then the dl is the width of, is a very small length, basically. So since we know that the centroid, the y coordinate of the centroid times L is equal to the integral of y times dl, we can plug that in to get the total area of this curve generated by rotating this curve along the x-axis is equal to 2 pi, the y centroid times L, as we see over here. Theorem 2 of Pappus-Guldinus. The volume of a body of revolution is equal to the generating area times the distance traveled by the centroid of the area while the body is being generated, as we see over here. So theorem 2 in more detail, the volume of a body of revolution is equal to the generating area times the distance traveled by the centroid of the area while the body is being generated. A way to understand this, we can rotate a rectangle along the y-axis or the x-axis, doesn't matter, to get a cylinder. The centroid of that rectangle is located over here. The centroid is rotated in a circle. The height of that rectangle is h. That centroid is located at height h over 2. We have r, the radius, and r over 2. So the volume of the body of revolution is equals to the height times r, which is the area of the rectangle over here, times 2 pi times r over 2, which is the circumference of that small circle over there. So as you can see, the volume of a body of revolution is indeed equal to the generating area times the distance traveled by the centroid of the area while the body is being generated. Because if we simplify this equation, we have we have pi r squared over h. No, pi r squared h, which is equal to the area of this circular area times the height. This is our more familiar definition of the volume of a cylinder. So generalizing this to integrals, the total volume is equal to the integral of 2 pi y times dA. 2 pi y is the circumference times dA is a very small differential element. Once again, the y coordinate of the centroid times total area is equal to the integral of y times dA. So we can plug that in to get the total volume is equal to 2 pi times the y coordinate of the centroid times the total area, which is summed up in this diagram over here. Thank you guys for watching this video on the two theorems of Pappus-Guldinus, and I hope this helped you understand centroids of revolutions and surface areas a little bit better. Thank you, and stick with me for the next video.